A warm welcome and greetings from IEEE Region 10. The IEEE Region 10 webinar series, IEEE Art 10 Talk, is pleased to invite you for the session on opportunities and challenges of integration of renewable energy in grids. This year, IEEE has embarked on this new initiative, that is the webinar series. Today we have with us Professor Cornelis Pickett from Adelaide, Australia, and Dr. Tahir Saleem Sheikh from Sindh, Pakistan. The webinar in particular is held in collaboration with Power and Energy Society to celebrate the PES week. The IEEE 10 Talk is a joint endeavor of IEEE Region 10 Industry Relations Committee, Art 10 Professional Activities Committee, Young Professionals Committee, Women in Engineering Committee, and Students Activity Committee. The primary objective is to focus on enhancing the awareness on trending topics to the community served by IEEE at large. With this, I would invite Professor Takao Onoe, Conference and Technical Committee Chair of Region 10, to make the opening remarks. Professor Onoe, please.
Thank you, Sanjay-san. Hello and good evening, everyone. My name is Takao Onoe. I'm the currently serving the Region 10 Conference and Technical Committee Chair. I'm very happy to be given the opportunity to providing some comment about the opening of IEEE 10 Talk, the second 10 Talk in the series of new initiatives of Region 10 in year 2021. As Sanjay mentioned, this is a very great opportunities to providing the value of the members to the members inside the Region 10 and worldwide with some seminar series on topical talks. So today's talk is about the renewable energy. That is very important for us right now. It is very, especially topical because we had, last week we had the Leaders Summit on climate with the many country leaders, including President Biden and many presidents and prime ministers from the Region 10 joined and then discuss about reducing the amount of CO2. So one of the key factor is the renewable energy to utilize some other power sources. So this is very topical, and then we are very happy to have the two premier speakers from the Australia and Pakistan. The professors Cornelis Pickett from the James Cook University, and then Dr. Tahir Saleem Sheikh. He's the CEO of the United Engineering Services from the Pakistan. So we are very excited having these talks, and then please enjoy the contents of the very cutting edge research and the development activities, and then even the several examples. Thank you very much for your kind attention. So please let us start our session. Thank you very much.
Thank you, Professor Onoe. Thank you. We now move on to the main agenda. That's the opportunities and challenges of integration of renewable energy in grids. And today we have two very experienced speakers. And the first speaker is Professor Cornelis Pickett, Adjunct and Associate Professor of the James Cook University and the University of Adelaide in Australia. We now move on to our next speaker, Dr. Tahir Saleem Sheikh.
Yes, I am here.
Dr. Tahir Saleem Sheikh is a qualified senior electrical safety and power quality engineer, having experience of 45 years in industrial sector, including 20 years in consultancy wing. He is presently the CEO of United Engineering Services, an electrical consultancy firm situated in Karachi, the capital city of Sindh province in Pakistan. Today, Dr. Salim Sheikh will cover power quality issues and smooth operation of the grid, which is very important and central to integrated power system. The consequences of poor quality can be catastrophic, leading to economic losses or at least life cycle damages. The methods for getting best power quality are implemented separately for each cause of bad power quality, like separate power supply feeder for harmonics producing loads, surge or deep absorbers for voltage surges, and etc. His lecture will address the introduction of power quality, its importance, assurance of best power quality. Dr. Salim's talk is expected to be a perfect foil to Professor Kikart's speech. Thank you, and over to Dr. Salim.
My name is Tahir Saleem. I am an electrical engineer, and the power quality issue is the most neglected part of electrical engineering. Nobody cares about it. Everybody says, I did service, power energy, that's all. And the result is that there are so many problems because of this poor power quality, because of poor design. So let's move on and see what happened. My presentation would be, the first part would be the general observation about the power quality, how to improve, and then the second would be the harmonics, its impact, its losses, and whatever it may be, and how to solve this harmonic distortions. In renewable energy also, you need this power quality phenomena very carefully. You have to adopt this power quality phenomena very accurately so that you can, as per IC 60034, you need a power of plus minus 10% tolerance limit. And as per IC 61000, it will give you the distortion limits, and the frequency would be plus minus 2%. So like a mineral water to a for your healthcare, for the healthcare of your power electrical units, you need a quality power within these limits, frequency as well as voltage. And this, your sine waveform should not be disturbed. So let's move on and see what happens. Yes. So there are so many phenomena in power quality: the voltage dip, equipment sensitivity, voltage unbalance, solution for voltage unbalance. I will tell you, flicker and its sources, effects of voltage fluctuations, harmonics, its effects, and solution. So we will see what happens. Electrical power is perhaps the most essential raw material used by commerce and industry today. It is an unusual commodity because it is required as a continuous flow. It cannot be conveniently stored in quantity, and it cannot be subject to quality assurance check before it is used because it is invisible. So you have to check yourself with the parameters. There are some limited statistics available on the quality of delivered power, but the acceptable quality level as perceived by the supplier and the industry regulator may be very different from that required or perhaps desired by the consumer. The most obvious power defects are complete interruption, blackout, which may last for a few seconds to several hours, and voltage dips or sags, where the voltage drops to a lower value for a short duration. Naturally, long power interruptions are a problem for all users, but many operations are very sensitive to even very short interruption like dips or sags. A few examples for the sensitive operations are continuous process operation. If I have the plant which has the continuous operation, a slight sag or dip will disturb the whole plant. Multi-stage batch operation, where interruption during one process can destroy the value of a previous operation, the whole plant may stop. Data processing, where the value of the transaction is high, but the cost of the processing is low, such as share and foreign exchange dealings. So what do you mean by power quality? A perfect power quality supply should be one that is always available, always within voltage and frequency tolerance, that is plus minus 2% for frequency as per IC code, and plus minus 10% for voltage. And as a pure noise-free sinusoidal wave shape, just how much deviation from perfection can be tolerated depends on the user's application, the type of equipment installed, and his view of his requirements. A voltage dip is a short-term reduction in a complete loss of RMS voltage. It is specified in terms of duration and retained voltage, usually expressed as a percentage of nominal RMS voltage remaining at the lowest point during the dip. A voltage dip means the required energy is not being delivered to the load, and this can have serious consequences depending on the type of load involved. Voltage sags, a longer-term reduction in voltage, are usually caused by a deliberate reduction of voltage by the supplier to reduce the load at times of maximum demand, or by an unusually weak supply in relation to the load because of the load shedding. What we call it is a load shedding. General cause, there are two main causes of voltage dips: starting of large loads, transients because of the large loads, either on the affected side or by a consumer on the same circuit, and faults on other branches of the network. Dips caused by large loads, when heavy loads are started like large motor, welding, and so on, such as large drives, the starting current can be many times the normal running current. Since the supply and the cabling of the installation are dimensioned for normal running current, the high initial currents causes a voltage drop in both the supply network and the installation. The magnitude of the effect depends on how strong the network is, that is how low the impedance is at the point of common coupling, and on the impedance of the installation cabling. Dips caused by starting currents are characterized by being less deep, much longer than those caused by network faults, typically from 1 to several seconds, or tenths of seconds, rather than less than 1 second. One solution for this voltage dip is to have a soft starter in circuit. This will drive, your drive will run on a ramp, and there will no much voltage dip on the system. And that solution is to negotiate within the supply company for a lower impedance connection. In our country, we don't have this concept, and this no utility can give you a low impedance connection. Equipment sensitivity. Characteristic of equipment sensitivity is electronic equipment power supplies, such as those used in personal computers and programmable logic controllers, PLC, employ a reservoir capacitor to smooth out the peaks of the fault, full wave rectified waveform. So they should be inherently resilient to short duration dips. The larger the capacitor, the greater the difference between the stored capacitor voltage and the minimum required for the internal voltage converters to operate, the better the resilience will be. Designers will always try to reduce the size of the capacitor to a minimum to reduce size, weight, and cost, while ensuring that the charge stored is just sufficient at minimum voltage and maximum load. For good dip resilience, a much larger capacitor is required, at least twice as large as to enable the equipment to ride through one cycle, and 100 times as large if 1 second ride through was required. An alternative design strategy is to keep the minimum input voltage as low as possible to maximize the hold-up time of the system. The hold-up time will be much greater with a 230 volt supply than it will be with a 110 volt supply. Variable speed drives can be damaged by voltage dips and are usually fitted with undervoltage detectors that trip at 15 to 30% below nominal voltage. Induction motors having inertia so that they may help to support the load during a short dip, regenerating energy as they slow down. They become a generator. This energy has to be replaced as the motor re-accelerates, and if the speed is reduced to less than 95%, it will draw nearly the full startup current. Since all the motors are starting together, this may be cause of further problems. Relays and contactors are very sensitive to voltage dips and can often be the weakest link in the system. It has been established that a device may drop out during dip even when the retained voltage is higher than the minimum steady state hold-in voltage. The resilience of the contactor to dip depends not only on the retained voltage and duration, but also on the point on the waveform where the dip occurs, the effect being less at the peak. A three-phase power system is called balanced or asymmetrical. If the three-phase voltage and currents have the same amplitude or phase shifted by 120 degrees with respect to each other, if either of both conditions are not met, the system is called unbalanced asymmetrical. International standard, for example, European standard 50160EN or the IC 1003X series, give limits for the unbalanced ratio of less than 2% for LV and medium voltage system and less than 1% for HV measured as 10 minutes value with an instantaneous maximum of 4%. However, this limit can be locally reduced even as low as 0.24% to 5% at the British side of the channel tunnel. The first and the most basic solution is to rearrange, redistribute the loads in such a way the system becomes more balanced. For certain applications, there is a possibility of reducing unbalance by changing the operation parameters. This you can do yourself. In order to reduce the influence of the negative sequence currents causing negative sequence voltage on the supply voltage, low internal system impedance is required. This may be achieved by connecting the unbalanced loads at a point with higher short circuit level or by other system measures to reduce the internal impedance. Another type of mitigation technique is the use of special transformers, such as Scott and Steinmetz transformers. Finally, special fast-acting power electronic circuit, such as static varistor (VAR) compensator, can be configured to limit the unbalance. These are expensive devices and only used for large load, for example, arc furnaces, when other solutions are insufficient. VR capacitors are used on the transmission lines. Flicker, it is a symptom of voltage fluctuation which can be caused by disturbances introduced during power generation, transmission, or distribution, but are typically caused using large fluctuation loads, either loads that have rapidly fluctuating active or reactive power demand. The primary cause of the voltage changes is the time variability of the reactive power components of the fluctuating loads. Such loads include, for example, arc furnaces, F-rolling drives, etc. In general, loads with a higher rate of change of power with respect to the short circuit capacity at the point of connection to the supply. It is very important to note that small power loads such as starting of induction motors, welders, boilers, power regulator, electrical saws and hammers, pumps and compressor cranes can also be the source of flicker whenever the transient will occur. Voltage fluctuation in power system cause several harmful technical effects, resulting in disruption to production process with substantial cost. However, the physiological effect of flicker is the most important because it affects the ergonomics of the production environment, causing operator fatigue and reduced concentration levels. Electric machines, voltage fluctuation at the terminals of induction motor causes changes in torque. The torque will vary, and there will be the humming sound in that and slip, and consequently affect the production process. In worst case, they may lead to excessive vibration, reducing mechanical strength and shortening the motor service life. Voltage fluctuation at the terminals of the synchronous motor and generators give rise to hunting and premature wear of rotors. They also cause changes in the torque and power and increase in losses. Static rectifier. The usual effect of the voltage fluctuation phase control rectifier with DC side parameter control is a reduction of power factor and the generation of the non-characteristic harmonics and interharmonics. They come to it later on. In the case of drive breaking in inverter mode, it can result in communication failure and consequent damage to the system components. Electrolyzer. Both the useful life and the operational efficiency of electrolyzer equipment can be reduced in the presence of voltage fluctuation. Also, elements of the high current supply line can become significantly degraded, thereby increase maintenance or repair cost. Operational efficiency of all heating equipment is reduced in the presence of significant level of voltage fluctuation. For example, an arc furnace would require a longer melt time. So, this is a simple introduction about the power quality impacts and what type of the power quality is there. Now we come to the harmonics, which is the most typical and difficult to rectify because it will be costly for you to do some install something to reduce this harmonics level. So we have to be ourselves within the limits of the harmonic. We'll see what happens over there. Harmonic is a generalized term used to describe the distortion of a sinusoidal waveform by waveform of different frequencies. Non-linear load changes the sinusoidal nature of the AC power current and consequently the AC voltage drop, thereby resulting in the flow of harmonic current in the AC power system that can cause interference with the communication circuits and other types of the equipment. So this diagram, which will disturb by harmonics, the harmonics will create frequency multiple of the base frequency. These harmonic current also lead to increased losses and heating in numerous electromagnetic devices, motors, and transformers. When reactive power compensation in the form of a power factor improvement factor is used, resonant condition can occur that may result in a high level of harmonic voltage and current distortion when the resonant condition occurs at a harmonic associated with non-linear loads. Now, common source of harmonic is all linear loads. All non-linear loads in power system include power electronic converters, arc furnaces, induction furnaces, static VAR system, inverters for distributed generation, AC phase controller, cycloconverters, AC-DC converters, rectifiers commonly used in switch mode, power supplies, and pulse width modulation (PWM) motor drives. The effects of harmonics in a power system are pervasive in that they influence system losses, system operation, and system performance. Unless the harmonics are controlled to acceptable limits, as described by the IEEE and IEC standards, the power equipment and even more so, the electronic equipment may be damaged, resulting in costly system outage. The effects of harmonics are due to both current and voltage, although current produced effects are more likely to be seen in day-to-day performance. Voltage effects are more likely to degrade the insulation and shorten the life of the equipment. The following are some of the common effects of harmonic: increased losses, pulsating and reduced torque in motors, rotating equipment, premature aging due to increased stress in the equipment, increased audible noise from rotating and static equipment, misoperation equipment sensitive to waveforms, substantial amplification of current and voltage due to resonance, communication interference due to inductive coupling between power and communication circuits. I have so many examples in my country where these phenomena happens. Most power system circuit elements are primarily inductive. Therefore, the presence of shunt capacitor used for power factor correction or harmonic filtering can cause cyclic energy transfer between the inductive and capacitive element at the natural frequency of the resonance. At this frequency, the inductive and capacitive reactance are equal. In practical electrical system power factor correction, capacitors are primarily utilized to offset the power factor penalty imposed by the utility. In Pakistan, it is 0.9. This can create an abnormal situation because the combination of the capacitors and inductive elements in the system can result in either series or parallel resonance or a combination of both, depending upon the system configuration. Usually, parallel resonance occurs more often because capacitor banks are in parallel with system impedance. Inductive, this can be a matter of concern if the resonant frequency happens to be close to one of the frequencies generated by the harmonic sources in the system. The result of a series resonance may be the flow of an unexpected amount of harmonic current through certain elements. A common manifestation of the excessive harmonic current flow is an aberrant relay operation, blown fuses, and overheating of cables. The result of a parallel resonance may be the presence of excessive harmonic voltage across the network elements. A common manifestation of excessive harmonic voltage is capacitor or insulation failure. Because managing harmonic in a power system is considered a joint responsibility involving end users and system owners to operate, harmonics limits are recommended for both voltage and currents. The acceptable voltage distortion level from the basis of the harmonic voltage limit is the figure on the next slide. The recommended limits in this clause apply only to the point of common coupling and should not be applied to either individual pieces of equipment or at a location within a user's facility. In most cases, harmonic voltage and currents at these locations could be found to be significantly greater than the limits recommended at the PCC due to the lack of diversity, cancellation, and other phenomena that tend to reduce the combined effects of multiple harmonic sources to levels below their algebraic summation. Now, this is a standard for harmonic limits in IEEE standard 5192 and 2014. You can see this chart. This gives you of different environments, and different environments, the harmonic limitations are different. So, this is are the voltage distortion limits. But coming to this slide, we will discuss this. But this gives you a complete phenomenon. The typical environment is what is the acceptable limit for computers and power sources. So what should be the line frequency tolerance limit? Whereas the plus minus 2% Apple IEC 60034 and plus minus 10% is the recent voltage tolerance limit, power source tolerance low. These are the different figures. You can check it out over here. So the transient pulses, ground current, how much should be the ground side, the leakage current, maybe the voltage deviation, how much different environment. We are using electronic sensitive equipment. So the 0 to 2% total RMS, 0 to 10%, 5 to 10% largest, and generally, we will come to that slide over there. 5% maximum total voltage regulator signal circuit is the solution for that. Now this is the IEEE standard 5192014, which give a different voltage level and what to the individual harmonics limits. Globally, their multinational companies, they set their limits as per ICA and IEEE standard. So for the total the voltage harmonics, the limiting value is 5% and the current harmonic is 10%. THD value, this is called the total harmonic distortion. So high voltage system can have up to 2% THD where the cause is an HVAC terminal whose effects will have affluent and points in the network. The future users may be connected. Current distortion limit for a system rated 120 volt through 69 kV. This is IEEE standard 59201 for recommended current distortion limit. So you have to operate either as a renewable energy or conventional energy within these limits, so avoid any defects in the equipment. Maximum harmonic current distortion, what should be there? So at this is the ratio given over there, distortion in present of IL. So we give you the chart. Maximum harmonic current distortion percentage of IL, total current distortion limit for system rated high voltage, for high voltage. Harmonics order limit 25% of value given in table 2, table 3, and table 4 for that particular standard and codes. Now, as per IEC standard 61002-4, they have electromagnetic environment divided into 3 classes: class 1, class 2, and class 3. And this class applies to protected supplies and as component levels, though in public networks. And class 2, this class applies generally to PCC and IPCs in the environmental industries. And class 3, this class applies only to IPs in industrial environment. So if I tabulated this in this way, the compatibility level of harmonics, different harmonic level, and the easiest one is that the class 1, class 2. So total harmonic distortion should not be more than in class 1, and class 2 it should not be more than 8%, and class 3 should not be more than 10%. So you have to arrange your non-linear loads accordingly as per design to reduce this level so that no special, corrective equipment need be required to operate. So this is the class 1, 65%, class 2 is the 8%, class 3 you can go through the presentation and find out what covers the class 1, what covers the class 2, and what covers the class 3. So this we have discussed it out: harmonic distortion, blackouts under and over voltage dips and surges, and transients. Now I come to that. That's different solutions simultaneously. The capacitive reaction decreases, the frequency increases. A relatively small percentage harmonic voltage can cause a significant current to flow in capacitor circuits. Presence of harmonic current causes distortion in waveform. If the natural frequency of a capacitor bank power system reactance is close to a harmonic, then partial resonance occurs with the amplified values of voltage and current. The elevated current will cause overheating. Possible solution, maybe one of the easiest solution is oversize component by 1.3 to 1.5, increase insulation level, and then third would be the harmonic factor, which is the and reactors, which is the costly affair. In generators, if you are operating generators, there would be thermal losses, effect on sequence components, voltage distortion, line notching, and generators. Transformers will have a thermal losses, unbalanced distribution, transformer and neutral current. And for selection of the transformer in environment of harmonic distortion, you have to calculate the K factor. This is called the transformer D rating or K factor for transformer. And if you are ordering it in transformer for a harmonic distortion environment, then you can have this K factor calculation and find out what should be the K factor and select your transformer accordingly. Induction motor, again, in this, the thermal losses will increase, effects of harmonic sequence component, an explosion proof motor, and voltage distortion. If you have an induction motor of certain temperature classification, T1 to T6 are the classification for hazardous area, then if you use this in such an environment where the temperature, this will destroy the sleeves of the motor and the temperature classification will change and will not become a hazardous area motor. So you can see over here in explosion proof motors, they are designed on pure sine base. You order it. The rotor may overheat due to harmonics resulting hot rotor and damage of seals. And temperature exceeds the T class. WXD, WXC, WXV, WXN, according to EN 60034, 2% voltage distortion is permitted. 3% voltage distortion is permitted for WXN as per EN 60034-20. So you have to be very careful when you are using your equipment exposure to atmosphere. The environment will have too much effects on these components. A voltage harmonic cause extra losses in the direct line connected motor. And for VFD, the fifth harmonic create a counter rotating field, whereas the seventh harmonics create a rotating field behind the motors. Synchronous speed, the pulsating torque causes wear and tear on coupling and bearing. General use of the increased use of VFD create this type of a fault for induction motors. So there were so many other effects also: variable speed drives, lighting, flicker, effects of line notching on lighting, potential for resonance, uninterrupted power supply, computer and computer-based equipments. Thermal losses, skin and proximity effects, neutral system in 4-wire system, additional effects associated with the harmonics, effects and negative consequences, conductor or overheating skin effect, depending on frequency, capacitor failure, faulty operation of fuse and circuit breaker, increased stray losses in transformer resulting increase in iron, copper and eddy, increased losses in generator, multiple zero crossing effect, the timing of the voltage regulator, causing interference and operation stability, incorrect recording by utility meter, that is very important, misoperation of drives, interference in computer and telephones. Now, this is a certain, you can see in this example, the harmonic current increased by 42% and the losses increased to 17.73%. That's why the thermal losses increase in the cable. Sometimes the cable bursts. I have seen that. So with very big plants also. I have seen this, the bursting of the cables. Measurement, you can have a problems in measurement, peak factor, peak value, form factor, RMS measurement is based on an average reading, and whereas this will have a misappropriation reading to your meters. Measuring equipment, telephone, circuit breaker, fuses, relays, noise stripping of fuses and relays, radio, audio and video equipment, capacitor. Even I have seen in certain hospitals the harmonic creates so many noises stripping and image distortion in ultrasound labs. So you have to correct this thing. If you come to an ideal power quality, that this is a picture taken by us, our spectrometer, that says that the power quality, the above is the voltage and the lower is the voltage line of current, and THD level varies 1.4, 1.3 and 1.2, 6.9, 7.3 and THD 6.8. So this is idle and this is a defective operating at the FD. And you can see over here, the power is not much, but the current harmonics is 36.5, 37.7. And the third phase, there is some problem in connection. So I will not discuss 37.7, but they give you 37.6. This is very high. Normally it should be not more than, if as per global standards, should not be more than 10%. If the environment is very critical for power electronics equipment, it should be more than 5%. So I see 6 other frequencies which are not integer of the multiple frequencies. They are called subharmonic, whose frequency is less than the fundamental. We will not discuss in this presentation about the interharmonics, but they also create problems in interharmonics problems. So now, what are the linear loads, resistance and induction motors? Non-linear loads may be induction furnaces, variable drive. We have discussed it earlier, speed drive, solid state, soft drive, instrumentation, computer, and so on. This are the non-linear loads which disturb the power factor. And this is the example of different base frequency is taken is 50 Hz. So harmonics are represented frequency, multiple fundamental of frequency. Harmonics are designated by the harmonic numbers of multiple of frequency. And you will see total harmonic distance is calculated as the sequence of all harmonics divided by the normal frequency. This gives you the formula over here. Now, the one solution for this is to increase your power equipments. So in this case, there is a transformer which gives you 10% THD voltage excess. And if you increase the size, it will reduce to 2%. And generally, it is a general practice that you should not increase a non-linear load on a transformer or a generator more than 20%. This yields RMS value of distortion as percentage of the fundamental frequency. This condition is called a non-linear load, a non-sinusoidal load. The total amount of harmonic will determine the THD of the non-linear load. The more sources impedance, the more voltage distortion. Generally, in general practice, the allowable limits of current voltage, so many global multinational companies have set its limits. The voltage harmonics is 5% and current harmonics as 10% is the best maximum limit. Otherwise, we have to go for that. So these are some of the basic solutions for that. The basic solution is the position the non-linear levels upstream, up remotely from the source. This figure gives you Z1 is the impedance for non-linear loads and Z2 is the sensitive loads. So we have to place them. There will be, you have to decide with the spectrum of the harmonic solutions, harmonic spectrum. What solution is your the best? How much to invest in this? That is your own decision. So this is the one solution that you position the non-linear upstreams, then group the non-linear loads. That is, the non-linear you will have a separate bus bar for non-linear loads and for separate bus bar for sensitive loads. This is a general phenomena. You will have a separate source. The third would be that you have a separate source for non-linear load and linear loads, which I've seen in Karachi, a problem in a foundry. In a foundry, I have found with the induction furnace this phenomena. They connected this non-linear load as linear load, a single bus bar. The source is 11 kV, the medium voltage, and there's a lot of problem for that. So they have to separate this source of power, the ambient network, with two sources. They have to do it. And then the non-linear will have a separate panel and linear load will have a separate panel. These are the split transformer. I have seen that, but in spite of the fact there is a lot of problem. DYD connection suppress 5th and 7th harmonic, which is the important phenomena generating from a VFD. A DY connection suppress the 3rd harmonic, which is the important phenomena for a UPS, and a DZ5 connection suppresses the 5th harmonic, 5 and UPS, both, whatever it may be. So you can see The UPS in positive direction gives you the harmonic current, a third harmonic. This third harmonic means the multiple of the base frequency. Fifth harmonic as seventh harmonic means the multiple of the base frequency. Yes. This is also very mostly people installed in our country the filters, but forget about the earthing because all this noise level have to go to the grounding. So there would be three networks are recommended by the standards and codes in the all over the world: TT, TNC, and TNC and IT. So TNC will represent a neutral and ground common phenomena in the distribution network, and TNS will have a neutral and ground separately from the source. The source will be neutral and ground will be the same. The source will be connected, and apart from that, if you're going further, the TNS will have a separate earthing circuit, and TNC will have a combined effect. So the power circuit, we will recommend the power circuit. TNC is normally recommended, and TNS for harmonic suppression is recommended. And for critical load IT, where the neutral is not earth, and the IT and the single fault will not trip your circuit breaker, and the IT and the second fault occurs double fault, the IT breaker will be tripped. So there are certain limitations. So you should have a good grounding for surge protector as well as harmonic distortion limitations. So a filter, if you install a filter, this is very expensive. So its filter would be, what filters are, you can see over here. This is a passive filter. The reactance and capacitance is connected to nonlinear load, and this nonlinear load noise is filtered out through ground, and the pure sine wave goes to the linear load. This is a passive filter, and in industrial installation with a set of nonlinear load representing more than 200 kVA variable speed drives, UPS, etc. This installation requires power factor correction, installation where voltage distortion must be reduced to avoid disturbing sensitive loads, installation where current distortion must be reduced to avoid overloads. Active filter. This active and hybrid filters are very expensive. For nonlinear loads of less than 200 kV installation, current distortion must be reduced. The simplicity is that a nonlinear what type of third, fifth, seventh, 11th, whatever it may be, generates linear. Countered in opposite phase, this harmonic generation unit create the harmonics level, which nullify the impact of the one phase and second and cross phase, and give you a simple noise-free linear load and simple sinusoidal waveform to lower linear loads. So this is called an active filter or sine filter also. This is very expensive. So principle, this is the simple waveforms over here. And this installation is more than 200 kV hybrid filter. It is a combination of active sine filter as well as passive filter. The combination, whatever remains with the active sine filter, this hybrid filter will correct them with sensing device to create the same harmonics, and which will nullify the impact of the harmonics on linear loads. So this is installation more than 200 kV. Harmonic, and whenever you have to decide, harmonic audit will determine the exact method. You can say anything. Non-linear should not be more than 20% of a transformer or generator. This is the general practice. And the harmonic correction, they give different harmonic calculation. You can do it over here. This is an example of harmonic calculation. You can do it yourself manually, but the soft starters and the software, whatever it may be, ETAB or Equidale, whatever it may be, they use the direct harmonic distortion coming out of the distribution circuits. You can use that. This for example. Transformer short circuit current, transformer full load current, generate. These are the different harmonic calculation. Now I come to the conclusion. Power being an important commodity must be supplied to the consumer with best quality as much as possible so that unwanted distortion in the supply to the equipment is prevented. Poor power quality is not only damage the equipment, but also it interrupts the whole operation of the workplace. The solution for maintaining power quality are expensive, but they can be implemented subject to cost versus output ratio. In textile sector, your product disturbed, the product quality disturbed. So there are so many things. I have seen in a hospital, they built, which is a very big hospital, they built an ultrasound lab. The images were disturbed because of the UPS third harmonic. We analyze it. The third harmonic create noises which create disturbed noises in the patient's images. So what was the conclusion is that the UPS was without a built-in filter. So they connected it to another UPS and the problem was solved. This UPS was without a built-in filter. So whenever you install a UPS for this type of the harmonic distortion, you have a built-in filter or install a separately filter of whatever type you may be required. And proper earthing, whatever I have said is TNS, means neutral and ground cable should be separately run across the whole distribution company. The immediate discharge, I have seen the Navy, in the Navy also, in the dockyard also, they convert this, this is one example, they install a generator and motor to convert 60 hertz to 50 hertz and the whole board electrical power disturbed due to the VFD stored in the boat. So they have to change it with the 50 hertz and the loaded. So say they have a radar system in the boat and they have to change it to 60 hertz radar system. So these are the one problem. The solution for the maintaining power quality are expensive, but they can be blend subject to cost. You have to see yourself. But in our country, I have seen the industrial sector is most negligent on this issue. So they have a lot of problems in this of the harmonic distortion. And sometimes the motor burns, transmission line burns, and AIA, automatic AVR burned of a generator, if you have a standby generator. So you have to be very careful in giving the power energy to your equipment. So these are the certain filters installed in the power plant. You can see this is an analyzer over here, different types of analyzer. So thank you very much for giving me an opportunity for this presentation. So if any question arises, I am ready to answer here.
Thank you, sir. We will just have a few minutes for the questions. Let the questions come. We can share with you.
So there's a few questions here. The first question is, how would the third harmonic distortion caused by the single phase motors and the rectifier supplies? Other users and the current balance in grid can still use 3.5 crore cables for 380 by 415 volts, 50 hertz, 3 power 4 volts distributed systems.
In fact, it depends on the motor power rating. And you have to, how would be third harmonic distortion caused by the single? What is the question? What is the question?
Prashant, I would
the
request
question
you
is-
to kindly repeat your question because the sound is distorting.
Yes, so the question is, how would the third harmonic distortion caused by single phase motors and rectifier supplies affect other users and current balance a grid?
Yes, it can affect the direct other grids also. So you have to correct accordingly. The most important phenomena in this, the easiest, the simple way is to connect with the TNS system so that it can absorb mostly all the noise levels and the distortions in the ground.
Continuation, sir. Continuation of this, can we still use 3.5 4 cables for 380 by 415 volts, 50 hertz, 4 watts distributed system.
Yes, you can use it. But the size of the cable depends on the rating of the motor. A single horsepower 3.5 is enough. Even the 2.5 is enough. But
Okay, sir.
if the environment is harmonic distorted, so you can increase the size of the cable, so that you nullify the thermal effect, the thermal heating of the cable. The impedance will be low if you increase the cable sizes, and the thermal heating will be less.
Yes, sir. Thank you, sir. There is another question, sir. Are static work?
Go on, please.
Yes, sir. Are static work compressors suitable for grid voltage imbalance?
I would the harmonic distortion.
Are static work compressors suitable for grid voltage imbalance?
Could not understand your question. But
The question is,
static
I'm making it clear. Are static works, HVCs, suitable for grid voltage imbalance?
Yes, they are used in transmission line. When CR on their transmission and they are installed at different levels of the transmission line for high voltages.
Okay. Prashant,
So
any further questions can you see?
So the final question, sir.
Yes.
The specified distortion limits of 5 by 8% are for rated current and watt duration. Are higher limits applicable for short duration?
It's applicable for everywhere. Duration will be the long run as well as the small one. You have to limit this within that limit. 5%, 8%, 10%. This is the IC code, and IEEE also gives you. So globally, you can reduce yourself have to limit itself to 5% to 10%. There is no limit to duration.
Sir, one final question, sir. A tuned LC filter has to be connected across 25 kilowatt supply for electric transition to improve power factor by draining out third harmonic. When periodically rectifier locomotives were in service, initial solution of PFA failed due to overheating of capacitors. What would be the situation?
So you have to increase your capacitor size. There are the capacitors available with resonant circuit, so they will reduce the resonance also. And other solution is to you increase the capacitor voltage and capacitor size. So they will solve your problem. Instead of 400 volt, you can go for a capacitor of 500 volt. Instead of 20 microfarad, 50 microfarad, you can go for 75 microfarad.
Sanjay sir, the questions are done, sir.
Yes, I think that's okay. Thank you, sir. Thank you very much. Thank you, Professor Salim. Thank you.
Thanks a lot. Thanks a lot.
With this, we come to the last and final leg of today's webinar, and we have with us Dr. Nirmal Nair, and I would request Dr. Nair to kindly propose the vote of thanks. Dr. Nair, please.
Thanks. Can you hear me, Sanjay? Hello?
Yes, yes.
Yeah,
yes,
okay.
Yes, we can hear you. Yes.
Okay, then. Thanks. First of all, I would like to thank all the attendees of this 10 talk, which has been organized by Region 10. So first of all, thanks for coming to this session. And I have a few people to thank, but I'll first start with the speakers themselves. So the first is Professor Keith Kirkwood. And he basically talked a little bit about how his country, Australia, and particularly his region, South Australia, is undergoing an energy transformation, and they're going for higher penetration of renewables. And he mentioned something about solar and wind, and with increasing penetration that way. The opportunities and challenges which he did were mostly around markets, electricity markets, the cost of electricity, retail electricity in his jurisdiction. And there was some interesting discussion about as the transition goes, there will be a little bit of challenges about how do you handle energy poverty, how do you handle essential services of the grid, and things like that. So I think that is just the flavor of all those countries in the world which are going through these energy transformation towards renewable. So I think Professor Keith kind of outlined that in a practical context about what it was, but I think he ended with an optimistic note that it is going to be 100% renewable, and you can operate a system with 100% renewable, which we have to look at how it can be economically done and how it can be securely done. So those are two different aspects. And he brought in the elements of storage and inverters and things like that, which would all have to be faced by the energy operators. So I would like to acknowledge his insight, and also that gives you a flavor of IEEE. IEEE in particular looks at technologies which are going to come in the next 50 years. Right. So I think he set us a challenge for all those power engineers and other engineers to watch the space. So thank you, Professor Kirkut. And there is a special memento, as you can see on the screen. I next move on to the next presenter, Engineer Tahir Saleem Sheikh from Pakistan. And I think this was an interesting presentation about an engineer who has been in the field for 45 years. And he talked about voltage quality, even though we call it as power quality. I think he started with some of the key attributes of what needs to be supplied from viewpoint of acceptable power supply to consumers, as well as PCC points and things like that. So I think he set the tone. It was a great tutorial coming through the basics all the way through to the techniques, the mitigation methods, and I think he spent a lot of time on the harmonic side, but then he quickly brought into the flavor of IEEE, which is the standards, right? So I think standards is a key part of IEEE. And as you can see in the acknowledgement, it is PES Day. So he's coming from Power and Energy Society expertise. So that was really interesting to see. But also he brought in some practical context about what can be done and his experiences about the challenges of mitigation, the expenses back again to power quality and things like that. But most of them were load centric. But I think if you kind of put that with Keith's presentation in the future, these establishment would have to look at how to allocate with solar inverters, battery inverters, and things like that. Even though he had some stories about some of the aspects around UPS and how people try to cut cost with buying cheaper UPS, but you can't do that in a sensitive application like a hospital, for instance. So I think it's an intermix of the interaction between capacitors and inductors and the exchanges of power systems, which is basically electromagnetic in nature. So that was neatly kind of tied about, and I think that was a good flavor about IEEE itself, which is practiced by industry people. So once again, thank you, Engineer Tahir Saleem Sheikh, on behalf of IEEE Region 10 and on behalf of PES and other societies which are supporting this part. So once again, a small memento on behalf of us. It's just a mug, and I think some special memento which will be posted to you. Lastly, but not the least, I would like to thank Mr. Sanjay Kar Chowdhury. He was the moderator for this session, and also he has been in the industry for quite a long time. He's now come to volunteer for us as part of Region 10, and he is the industry chair, and he's trying to bring a flavor of the industry chair, even though during these troubled times, which is his country in India and all across the world people are facing. But it was great to see him organize this panel. And interestingly, also Region 10, even though he's the industry IRC chair, I would like to give a shout out to all the other chairs. I think there is professional activities chair here, and I think young professional and women in engineering and things like that. So I think this is a new tone for bringing in all these organizations together to give reflections across the Asia Pacific region. And So I would like to thank Sanjay for pulling all this together in a virtual format. So I think I have finished all my thanks, I think, Sanjay, or is there anyone else I need to thank? Oh, yes, of course. These are the people, as I mentioned, Sanjay Kar Chaudhary, Professor Prakash Lohana from Region 10 Professional Activity, Akila Vijayatunge, who's managing this webinar coordinator. There was some hiccups. I hope you can apologize for us from the panelist side, but I think we had an interesting talk. And also Ashwant for the graphic design, whatever you're seeing on the screen, and the publicity notice by him, by Mr. Hisham, also a graphic designer, and Kanita Tukachamakaran, I think I got it right, the tech leader from content editor, Renu Guntar, also a content writer, and Sai Prashant for the webinar technical arrangement. I think everything has jumped to. I'm here in New Zealand, as you can see, so it's a wide spread of countries which are participating here. So these people together represent IEEE Region 10 Industrial Relation Committee, IEEE Region 10 Professional Activities, Young Professional, Women in Engineering, and Student Activity Committee all put together. So once again, thank you for your patience. I think we are at the end. There is a feedback, and I think it was in the chat window. If you could just flick that, that will be appreciated. So hopefully we would do one of these Region 10 talks in the coming months as you go through. But before I end, I would like to acknowledge, stay safe and be kind to each other. And I hope we should ride through this this pandemic, ravaging pandemic again, and hopefully, all of you get vaccinated soon, and we might meet in the coming few months or years, in person. So with that, I think we'll close this session, and I'll pass it on back to Sanjay if he has some parting word. Thank you.
I would request all of you to please stay back for a moment. We have a photo session, and would request all the panelists and all those who are present to switch on their video cameras so that we can have a group photos. Thank you very much. Prashant, you can have the group photo, please.
Sure, sir. I request all panelists to turn on the group for the group photo. On a count of 1, 2, 3. 1 minute. Taken, sir. Thank you so much.
It's taken, Prashant. Deepak ji
Yes,
was
sir.
not there.
Taken,
Deepak
sir.
ji, Amy. Okay.
Yes,
Thank
sir.
you very
Everyone
much.
others.
Thank you. Thank you. See you. Good night. Have a nice week ahead. Today is Monday. We have the whole week left. Thank you very much. Thank you.
Thank you very much.
We shall connect again next month. Thank you.
Thanks a lot.
Thank you very much to everybody. I think 26 people remaining there.